Swayam Prabha. Digital India. Educated India.
taking its derivative and showing that it's bounded. It is also very easy. I can take many derivatives further. This will always be bounded. Yeah, because you'll always get terms in E1 and E2, which are already known to be bounded. Okay, excellent. Right. So with this, with the Bar-Blatt's lemma, we have proven that the derivative of E2 also goes to 0. Right. So we've actually taken a nice formal procedure to prove that. After we've proven that E2 goes to 0, we've made a nice formal process to prove that E2 dot also goes to 0. We didn't just conclude it, just like that. All right. Okay, great. So once I have E2 dot goes to 0, the rest of the proof is not difficult at all. Why is that? I immediately claim that E1 also goes to 0. So look at the expression for E2 dot. It is minus K1 E1 minus K2 E2. And here I know, right, that the limit as t goes to infinity E2 dot is 0. And I know that limit as t goes to infinity E2 is 0. So what do? I can simply take limit. Apologize. I simply take the limit as t goes to infinity of both sides, right? And they have to match because I have an equivalence here. Yeah. If I say a is equal to b, a function a of t is equal to function b of t, then the limit as t goes to infinity cannot be different, right? Therefore, if I take limits on both sides, what happens? I know that this guy is going to 0. I know that this guy is going to 0. So the only way that the left hand side can go to 0 is if this quantity is also going to 0. And k1 is just a positive constant. So this is possible only if E1 itself also goes to 0 as t goes to infinity. Okay. Alright. So this is very important. Right. So what have we shown? We have shown with a bunch of steps, 9 steps to be precise. Yeah, looks like a lot of steps. But when your problem gets more complicated and you cannot resort to linear analysis, or you have an adaptive system which inherently makes your closed loop system non-linear, these 9 steps will look like a blessing to you. Yeah, as of now it looks like, oh my god, I could just have computed the eigenvalues and be done in a moment. But we took 9 steps. But like I said, when problems become non-linear and more complex, these 9 steps will be super easy, simple, significantly simple, or in fact just possible. Okay, the other steps wouldn't even be possible. Okay, excellent. So we have, as we planned, we've been able to show that E1 and E2 both go to 0 as t goes to infinity. All right. Of course, we could have used this Lyapunov analysis with LaSalle invariance. We've not done this still. Yeah. In this particular case, we could also have used Lyapunov analysis and LaSalle invariance. However, Bar-Blatt's lemma can be used in a larger scheme of things. So it's well known that this will work only for time invariant systems. Okay, work only for time invariant systems. Of course, there are modern versions which work for some sort of time varying behavior, but they're not all encompassing. Okay, so in general, LaSalle invariance principle, which again we are yet to cover, works only for time invariant systems. So if I have something like this where my gains, instead of being constant gains, they are time varying gains. Again, something that's not uncommon in adaptive control. Then only Bar-Blatt's lemma can be applied. These cannot be applied anymore. Yeah, only Bar-Blatt's lemma can then be applied to prove convergence. Okay. So, of course, this is a an exercise. Yeah, you are to prove convergence of E1, E2 to 0 using these similar steps. Any additional assumptions you're free to make, and but you have to state all these assumptions. You have to state all these. Now, I want to remind you that we've only proved convergence. So we have only we only completed the proof of convergence of these signals to origin. Okay, so we are saying something about the steady state behavior only. We are not saying anything about the transient behavior. Yeah, so remember this. Yeah, convergence only has been proven. Stability, or the fact that the trajectories remain bounded. See, one thing should be obvious to you already is that by step 2 here, let's see, by step 2 here, I mean, it's not like we have got nothing beyond convergence. We did get something more than convergence. We're also saying that E1 and E2 remain bounded. So all the closed loop signals. So notice that our trajectories we chose were themselves bounded with bounded derivatives. All right. So what does it mean? It means that if E1 and E2 are bounded, then X1 and X2 are also bounded. Okay. So we do have convergence from this, but we also prove that all our closed loop signals remain bounded. Okay. So this sort of thing that, I gave this funny sort of example, this cannot happen. This cannot happen. Yeah. This cannot go to infinity and come back. It can become very large and come back, but everything is still bounded. Okay. So all the closed loop trajectories are going to be bounded, and on top of it, you've proven convergence. Okay, so that's sort of the good thing. Okay, so remember, that's what we have. So we've completed the proof of how to use the Babolat's lemma to conclude asymptotic convergence of signals. Okay, stability is a separate question which we'll address slightly later. All right. So what did we do today? We continued our proof of convergence of signals using the Babolat's lemma, right? And we had finished, proving that a signal was L2. Then we proved that whatever terms appear in V dot, they converge to 0. That's the first thing we proved. Then we start off our next set of steps with the derivative of those signals that we proved already go to 0. And then from that, we prove that these derivatives of those signals are integrable by virtue of their convergence, and then that the derivatives are bounded. And from this, we can prove that the derivatives of signals that we proved were going to 0 themselves also go to 0. So if E2 goes to 0, we prove that E2 dot also goes to 0. Okay. And using the dynamics, that is how the equations of E2 dot look, we show that E1 itself also goes to 0. Of course, later on, we will also see where these things fail. Yeah. And we get into detectability obstacles in adaptive control. Okay. So we will discuss that soon. Right. Okay. So this is where we conclude today. Thank you for your attention.